Welcome back everyone. Today we talk about trigonometric substitution. We use this trick when we have to solve integrals involving square roots of sum or difference of square, like this one on screen. Algebraically, these are a nightmare. You can just split the square root, and please don't do it. A mathematician die all the time you do it. But trigonometry has a nice superpower, and to solve all your problems, all you need is Sohcahtoa. But what does it mean? So let's pick a half-square triangle with some angle theta. As you can see, it has three edges, one adjacent to the angle, one opposite to the angle, and the third one is called hypotenuse. Now, what does Sohcahtoa means? So stands for sine equal to opposite over the hypotenuse. Ka instead reminds us that the cosine is equal to the adjacent over the hypotenuse. And finally, Toa stands for the fact that the tangent is equal to the opposite side over the adjacent. With this word, you will be able to solve any integral with trigonometric substitution. Today, we will see three different examples and a more complicated one. Let's start.
Let's start with a basic integral. We are integrating 1 over x squared times the square root of 9 minus x squared. The important bit of this integral to focus on is the square root of 9 minus x squared. Why? Well, because now we are integrating something which has a factor of the form square root of a squared minus x squared, right? And in these cases, the correct substitution is x equal to a times the sine of theta. Why? Well, because if we go back to the square root becomes square root of a squared minus a squared times the sine of theta squared. We can factor on a squared and we get a times square root of 1 minus the sine of theta squared. And now we know that 1 minus the sine of the theta squared is equal to the cosine of theta squared. Taking the square root, this is just a times the cosine of theta. So basically, we simplified a square root into something which does not contain square root anymore. So that's why this substitution is really good. Now, let's compute the differential in general. So here we get the dx, so I take the derivative with respect to x of x, is equal to a times the cosine of theta times d theta. And now what we have to do is to use this change of variables in our specific situation where a is equal to 3, sorry. Perfect. So let's do substitution. We're gonna get the integral of dx becomes a times the cosine of theta d theta over x squared is a squared times the sine of theta squared. And now 9 minus x squared we have seen in this chain of equality, which is going to be equal to a times the cosine of theta, and for us a is equal to 3. So it's going to be only 3 times the cosine of theta. Oh, look here. So this a is actually a 3, and this a squared is actually a 9. Oh, great. So 3 cos theta and 3 cos theta, they do simplifies. So this is 1 over 9 times the integral of 1 over the sine of theta squared d theta plus a constant. And now, well, you have to remember that the integral of 1 over the sine of theta squared is just negative the cotangent of theta. And do you wonder where you can find all this integral? Well, you can just link to the link in the description and you're gonna find all the integral table that I prepared for you. So it's just gonna be equal to negative 1 over 9 times the cotangent of theta plus a constant. And here I put a constant before because I was ahead of me. Sorry for that. Okay. But now the problem is that we have to go back from theta to x. And here is when Sohcahtoa starts to be helpful. Indeed, let's remember that for us, we made a substitution x equal to 3 times the sine of theta. Okay? What does it mean? Let's rewrite it in another way. So we have that x over 3 is equal to the sine of an angle theta. And now let's draw a little triangle. So a little square triangle. This is our angle theta. And now from this expression, and remember it's Sohcahtoa, and the Soh part means that the sine is equal to the opposite sine divided by the hypotenuse, so h. This means that for us, this is gonna be x, which is the opposite edge, and h is gonna be the hypotenuse, which is 3. This means that the third edge is equal to the square root of 9 minus x squared by Pythagoras theorem. And why is this helpful? Well, because here now, you see you have the cotangent, and the cotangent is equal to the cosine over the sine. So this is 1 over 9 times the cosine of theta over the sine of theta plus a constant. And now here we can read cosine over sine. What it is the adjacent edge over the opposite edge, which means that for us this is going to be minus 1 over 9. The adjacent edge is square root of 9 minus x squared. The opposite edge is just x plus a constant. And that's it. Now, second integral for today, 1 over square root of x squared plus 4. So again, as before, we have to focus on whatever is under the square root. And here, the general form is x squared plus a squared under the square root. So in these cases, the correct change of variable is x equal to a times the tangent of theta. And why this is the correct one? Well, we can again go back to the square root. This is going to be equal to a squared, square root of a squared, times the tangent of theta squared plus a squared. I can factor again an a squared, taking the square root, this is just a, times square root of the tangent of theta squared plus 1. And now the tangent of theta squared plus 1 is just equal to the secant square. So this is going to be equal to a times the square root of the secant square, which is just the secant of theta. And if you don't remember what's the secant, this is equal just to 1 over the cosine of theta. So this is just equal to a over the cosine of theta. Okay? Good. Again, from a square root, we got something without a square root, which usually is really, really good. Now, what about the differential? Well, now we have to compute the x, so the derivative with respect to x on the left-hand side. This is going to be equal to a times the derivative of the tangent respect to theta, which is just 1 over the cosine squared, which is the same as the secant square. So this is a times the secant of theta squared d theta. Okay, great. So now we have to use this change of variables with a equal to 2. Okay, so a is equal to 2 in our case. Perfect. So the integral becomes, I'm integrating, dx is just a times the secant of theta squared d theta over square root of x squared plus 4. We did all this chain of equality, so we can rewrite it as a times the secant of theta. And here a and a simplifies, and also the secant simplifies up above and below. So we are left with the integral of the secant of theta d theta. And now, how do you compute the integral of the secant of theta? Well, this is one of the basic integrals, you have to remember it. This is just the logarithm of the absolute value of the secant of theta plus the tangent of theta plus a constant. And again, now the game is that we have to go back to x. And as before, we're gonna do it using the Sohcahtoa rules. So let's look at our change of variables. We put x equal to a times the tangent of theta, and in our case a is equal to 2. This means that x over 2 is equal to the tangent of theta, which is equal to the opposite side divided by the agents. Remember the TOA rule. And now let's report all of these on our square triangle. So the opposite sign is x, so this is x, the agent is 2, so this is 2, which means the third sign is, the third edge is square root of x squared plus 4, and this is our angle theta. Now, the secant of theta is equal to 1 of the cosine of theta, which means that is equal to the hypotenuse, which is square root of x plus 4 in this case, divided by the agent's edge, so in this case is 2, and the tangent of theta, well, is equal to the opposite sign over the agents, but we already written there, so this is x squared over 2. And now with these two equalities, we can rewrite our initial integral. So we're gonna get the final result is the logarithm of the secant is square root of x squared plus 4 divided by 2 plus the tangent, which is x squared over 2 plus a constant. So as a third exercise, we are going to do the integral of 1 over x square root of x squared minus 16. As before, we focus on the square root, which now is of the form square root of x squared minus a squared. And in this case, a is going to be equal to 4. So in these cases, the correct change of variables is x equal to a times the secant of theta. And why is that? Well, again, let's go back to the general square root. It's going to be equal to square root of a squared times the secant of theta squared minus a squared. We factor on a squared. This is a times the square root of the secant of theta squared minus 1, which, again, this is just the tangent of theta squared, and when I take the square root, this one becomes a times the tangent of theta. Perfect. So now we compute the differential, so we're gonna get the dx is equal to a times the secant of theta times the tangent of theta d theta, where this term is just the derivative of this one, and if you don't remember it by heart, you can always compute the derivative respect to theta of the secant, and you remember that this is just the derivative respect to theta of 1 over the cosine of theta, which means that you can compute it using the quotient rule. Okay, so now we made this change of variables in the specific situation where a has to be equal to 4, we said before. So let's do this change of variables. So we're gonna get the integral of 4 times the secant of theta times the tangent of theta d theta, so this is just the dx, over 4 times the secant of theta, which is x, and then for the square root, remember, right, we've done all this chain of equality, so we can rewrite it just 4 times the tangent of theta. Oh, that's great. Now I can simplify a bunch of them. So I have tangent of theta, secant of theta, secant of theta, and also 1 over 4. So this simplifies to 1 over 4 integral of d theta. This is great. This is an easy integral. This is just 1 over 4 theta plus a constant. And now I have to go back to x. So let's remember, we said that x was equal to 4 times the secant of theta. So x over 4 equal to the secant of theta. And I don't like to write the arcsecant, so the inverse of the secant. I prefer to write it as this is equal to 1 over the cosine of theta, which means that 4 over x is equal to the cosine of theta. And now I can invert both sides, which means that I apply the arc cosine on both left and right. So I get the arc cosine of 4 over x is equal to theta. So I can rewrite my integral as 1 over 4, the arc cosine of 4 over x plus a constant.
So, last exercise for today, this little monster, 1 over the square root of x squared plus 4x plus 13. So, it doesn't look like at all the other square root we've seen before, but we can reduce the situation by means of doing this little trickery, which is called complete the square. And I know this is something that you have not done for a while, but I swear it's gonna be easy. So what I usually do is the following. I pick up whatever is below the square roots and I rewrite it. So I have here x squared plus 4x plus 13. And then to complete a square, I do the following. I rewrite the x squared term. And then instead of whatever term is here in front of x, I rewrite it as 2ax, and I'm gonna add a squared, and I'm gonna subtract a squared, and I'm gonna finally rewrite 13 here in this case, plus 13. Okay, so I rewrote 4x and I put it 2ax, and then I add and subtract a squared. And why I do this? Well, now what I want to do, I want to equate the two coefficients of x, which in this case means that a has to be equal to 2. And now what I can rewrite our initial expression as x squared plus 4x plus a is equal to 2 plus 4 minus 4 plus 13. And now I recognize that x squared plus 4x plus 4 is nothing but x plus 2 squared. And then I can sum 13 and minus 4, and I get plus 9. what do I gain from this? Well, I gain that now I rewrote all this term as a sum of two squares. So let's see how this simplifies my integral. Let's pick up our initial integral. Let's copy paste it down below. So we've seen from before that this one we can rewrite it as the integral of 1 over square root of x plus 2 squared plus 9 in the x. Now I suggest you to do this substitution. You put t equal to x plus 2. You compute the differential, so you have dt equal to dx. So you can rewrite your integral as the integral of dt, because the dx is equal to dt now, divided by square root of t squared plus 9. So now we are back to a situation that we already encountered. So we have 1 over the square root of the sum of two squares. This means, again, that the correct substitution is t equal to the tangent, so 3 times the tangent of theta. And why 3? Because here we have 9, which is a square, which means that I have to take the square root of 9, which is 3. If I do this substitution, then I get that dt has to be equal to 3 times the secant of theta squared, which means that my integral becomes the integral of, d theta here, 3 times the secant of theta squared d theta. And from before, we know that all the square roots just becomes 3 times the secant of theta. So we simplify the secant and the 3. So we are left only with the integral of the secant of theta. So we have just to integrate the secant of theta d theta. And this is a well-known integral. This is just the log of the absolute value of the secant of theta plus the tangent of theta plus a constant. As before, we want to go back to t and then to x. So what do we do? We know that we made the substitution t equal to 3 times the tangent of theta. We can bring the 3 on the other side. And then we remember the TOA part of Sohcahtoa, which means that the tangent is equal to the opposite side over the adjacent. We draw our little triangle. So here we have theta. So this means that t is our opposite side, 3 is our adjacent, which means that the hypotenuse is square root of 9 plus t squared. And now we have to divide the secant using the triangle. So we remember that the secant of theta is equal to 1 over the cosine of theta. And the cosine of theta, we can remember the COA part. So the cosine is equal to the opposite over the hypotenuse, which means that for us it's going to be the hypotenuse over the secant is going to be the hypotenuse over the adjacent side, which in this case is square root of 9 plus t squared divided by 3. Great, so we can do the substitution again. So we have that the integral is equal to the log of the absolute value of the secant, which is 9 plus t squared over 3 plus the tangent of theta. Now we wrote it before, this is 3 over 3 plus a constant. And now we have to remember the last step, because at the very beginning we set t equal to x plus 2, which means that now
we can rewrite this integral as the log of the absolute value of the square root of 9 plus x plus 2 all squared divided by 3 plus x plus 2 over 3 plus a constant. So that's all I have for you for today. Thanks for watching, and I'll see you next time.